Humans are constantly traveling in time, and all at approximately the same speed, 1 second per second. Our telescopes help us look back in time. These are stars and galaxies, so far away that their light has taken years to reach us. When we look back at them, we only see what they used to be. But of course, when we think of time travel, we're talking about the possibility of traveling faster than 1 second per second. We're talking about exploring worlds and ideologies and people existing long before and after our time. But is that even possible? More than 100 years ago, Albert Einstein came up with an idea of how time works, and he called this general relativity. The theory states that time and space are linked together and that our universe has a speed limit. It can't travel faster than the speed of light, which is 186,000 miles per second or 299,792 kilometers per second. Considering this theory, the faster you travel, the slower you experience time. Philosophers have argued that relativity implies eternalism, the idea that past and future exist in a real sense, not just as events that occurred once or will occur sometime later. The idea is directly opposite to presentism, the idea that past and future exist only as changes that occurred or will occur and they don't have an actual existence of their own. If that is the case, there's no past or future to travel to. But those who choose to believe in eternalism view time as a dimension equal to spatial dimensions, and that future events are already there, just like different places exist in the same plane. While special relativity is enough to get us started in terms of moving through time, it doesn't give us a way of going back in time. It does, however, give us a way of going forward, and at a rate that we can actually control. In fact, thanks to special relativity, we can have a pair of twins of different ages. This phenomenon is the twin paradox. Consider this. One twin heads set sail for Alpha Centauri close to the speed of light, and his twin stays on Earth. Once home, the twin that left for another star system would have aged by a few years, but his twin would likely be a grandfather. Both would experience the passage of time the same way and wouldn't recognize the difference until they met face to face. Just like traveling at a high speed affects the rate at which time passes, being near a heavy object like a black hole will affect one's experience of time. To illustrate his theory, Einstein re-envisioned space itself. Instead of treating space as a flat and rigid place that holds all the objects in the universe, Einstein thought of it as curved and malleable, able to form gravitational dips around masses that pull other objects in. It's like placing a bowling ball in the center of a trampoline. Any smaller object placed in the trampoline will slide towards the center. The closer said object gets to the center of the dip, the faster it will accelerate. The center of the Earth's gravitational dip is located at its core, where gravitational acceleration is strongest. According to the theory, because time moves slower as you move faster through space, the closer an object is to the center of the Earth, the slower time moves for that object. But black holes are only the beginning of the story. Physicists have also speculated about the impact of much more exotic structure called a wormhole. Wormholes could theoretically connect one location in space-time with another. It would be like building a bridge from one region of space-time to another. But there's a catch. While we have overwhelming evidence that black holes exist in nature, wormholes are at best speculative. Building such a bridge would also require mass and energy, the likes of which we don't even know if they exist in reality. Yet we have extensively studied the theoretical properties of a wormhole. Scientists in Russia have tried using radio telescopes to detect them as well, but we still know little of how to form a microscopic wormhole, one large enough for a human or a spaceship to pass through. Some speculative theories of quantum gravity tell us that space-time has a complicated, foam-like structure of wormholes, a billion times smaller than an electron. Some believe it may be possible to grab one of these truly microscopic wormholes and enlarge it to a usable size. But the question is, even if we had a wormhole, would nature allow us to use it as a time machine? And even if it did, we have another dilemma on our hands. What happens to our understanding of cause and effect if backward time travel became possible? The most famous example to illustrate this conundrum is the grandfather paradox. A time traveler travels back in time to when his grandfather was a young man. He kills him, most likely on accident, which means his parent is never born. If his parent is never born, how could he have traveled through time? Over the years, many physicists and philosophers have attempted to find resolutions to the grandfather paradox. One possibility is that the existence of the contradiction simply proves that no such journeys are possible. The laws of physics must somehow prevent backward time travel. This was also the theory of Stephen Hawking, who called this rule the chronology protection conjecture. Or maybe backward time travel is actually possible, but time travelers don't have the power to change the past, no matter how hard they try.
But can we change things if we do it differently?
What's happened's happened. Which is an expression of faith in the mechanics of the world.
He might change their mind or shoot the wrong person, or circumstances could lead him to make a mistake. There wouldn't be a single ripple created in time. The closest mankind has come to figuring out time travel is with the help of a tabletop device illustrating the principles of a working time machine, made by Professor Mallet from the University of Connecticut. This device has lasers which generate a circular beam of light. The space inside this ring laser should twist, just like stirring a cup of coffee. Because space and time are intimately connected, warping space should also warp time. Professor Mallet's theoretical work has shown that, given enough laser intensity in a small enough space, it should be possible to alter the normally linear timeline we all inhabit. According to him, if space is being twisted strongly enough, this linear timeline is going to be twisted into a loop. If time all of a sudden is twisted into a loop, it allows us the possibility of traveling into the past. But in order to make it work, the concept would require vast amounts of power and a way of shrinking everything to a microscopic scale. And once we have a time machine, using it successfully will require a detailed understanding of time itself. Professor Mallet's model considers the idea that past, present, and future are all equally real, like in Einstein's theory. So you can think of everything that ever did exist, does exist, or will exist as all somehow being out there in space-time. But all physicists and scientists seem to agree on one thing. No one can quite manage to engineer a time-traveling DeLorean or a custom-built wormhole anytime soon. Much more work is left to be done, so they are now focused on completing the work Einstein started all those years ago. After more than 100 years, scientists still haven't figured out how to reconcile general relativity with the other great pillar of 20th century physics, quantum mechanics. Some believe that a long-sought unified theory known as quantum gravity will offer new insights into the nature of time, or at the very least, give them what they need to go just beyond general relativity to understand time. In quantum physics, nothing is impossible. Particles can even pass through walls. So could time travel really be possible? The human race is a curious one. When kept in the dark, we have the fantastic ability to concoct the wildest, most amazing stories. We will always daydream about having the freedom to move through time, just like we move through space. The world of quantum physics might just be the key to unlocking time travel, as this area of physics emerges at a very small scale, where the rules of classical physics we learned about in school textbooks break down. For example, in the quantum world, it is possible for a particle to exist in multiple places at once, and even if time travel is possible forwards in time, it will be nearly impossible to travel to the past. As Stephen Hawking once said, the best evidence we have that time travel into the past is not possible, and never will be, is that we have not been invaded by hordes of tourists from the future.